So it's my great pleasure to introduce a speaker, Professor Yang Shaohong. And so Professor Shaohong is a JR East Professor of Engineering and faculty in the Department of Mechanical Engineering, Department of Material Science and Engineering, and the Research Laboratory of Electronics at MIT. Her research is centered on using physical material chemistry to control kinetics and dynamics in processes of making zero carbon energy, chemicals, and fuels. Professor Shaohong is a member of the U.S. National Academy of Engineering, and she is a fellow of the American Association for the Advancement of Science, the Electrochemical Society, the National Academy of Inventors, and the International Society of Electrochemistry. Her work has been recognized and by receiving many awards, including Faraday Medal of Royal Society of Chemistry and the Dr. Karl Wamsler Innovation Award, and also Hamburg Prize in Chemistry. And she has advised more than 100 students and postdocs at MIT who are now pursuing successful career in industry, including Tesla, Amazon, and Apple. And in academia, including faculty position at MIT and academic position in Europe and Asia. And Professor Shaohong today is going to talk about a very interesting and meaningful talk entitled Addressing Scientific Challenges Towards Mitigating Climate Change. So we now welcome Professor Shaohong.
Thank you, Professor Liao, for the very nice introduction. I'm delighted to be here and be part of the celebration for the 30th anniversary for School of Engineering at Chinese University of Hong Kong. We're going to look at what challenges and opportunities towards mitigating climate change. Our planet is changing, and with warming of our planet, we see the extreme precipitation and the extreme lack of. And with this climate change, Asia would bear more of the impact because we have more of the world's population, but less of world's land. The climate change has been correlated with the global CO2 emission from our energy use. And Asia, US, and Europe contribute significantly to our global CO2 emission. So therefore, there is an urgent need to reduce our CO2 emission and shift to alternative energy technologies so that we can reduce our CO2 emission and stabilize our global temperature. Various projections have shown we need to reduce our CO2 emission very rapidly in order to stabilize a temperature rise of 2 degrees. So the task is on us to reduce CO2 emission. And it's challenging to reduce CO2 emission because emission come from multiple sources, right? It comes from transportation, it comes from power or buildings, and come from our chemical industrial processes. Which contribute roughly equally to our global CO2 emission. There's also opportunities with recent development and with the growth of solar wind. And now you can see that the electricity come from solar and wind is among the cheapest relative to other form of electricity generation. So the challenge would be, how do we essentially utilize more and more of electricity from solar wind in order to power our needs in transportation, in industrial processes, in power, and in buildings. Batteries, especially lithium-ion batteries, are poised to electrify light-duty vehicles. But the challenge is, how do we develop technology so we can electrify heavy-duty vehicles? How do we electrify aviation in order to mitigate and reduce CO2 emission in the transportation sector? In buildings, we need not only electricity, we also need heat, right? So combination of batteries as well as energy carriers so that we can provide power and heat is really important. So this is where electrolytic cells or technologies are important to store electricity in chemical form and generate energy carriers such as hydrogen or hydrogen containing small molecules that carrying energy, or generating metals, where we can either utilize energy carriers by converting them to heat thermochemically, or we can convert them electrochemically to regenerate work, and which there can play a very important role, either thermochemically or electrochemically, in order to reduce CO2 emission and replace fossil fuel utilized in power buildings or in industrial sectors, such as steel making, cement making, and ammonia synthesis. Some of these industrial processes intrinsically generate CO2, and therefore as negative emission technologies that can capture or convert CO2 to fuels is very important. So therefore, you can see in order to reduce our CO2 emission, to be able to utilize more of electricity from solar wind, three technologies: batteries, electrolytic cells, or fuel cells, as well as negative emission technologies, are key in order to enable and realize the decarbonization of our energy future. Lithium-ion batteries has, experiencing explosive growth in the transportation sector, and largely due to the reduction in the system cost, right? So you see from this graph, the system costs have been reduced over an order of magnitude, and is projected to further reduce as we increase essentially the scale of our industry, as well as innovation in new material chemistry or battery chemistry, right? So going to solid state lithium batteries or going to metal air batteries potentially further reduce the cost, allow us to utilize more of the technologies in our transportation, in our power, in our buildings. Now, going beyond batteries, right, where batteries store each electrons with each transition metal in the lithium-ion batteries, where it's difficult to decouple power and energy, we also need to think of how we can develop open systems, such as electrolytic cells, where we can generate and use energy carriers, such as fuel cells, electrolytic cells, or flow batteries, where we can decouple power and energy, right? So you can actually have a sizable fuel cell stack or electric cell stack, where if you want to scale up the energy, one can essentially generate or increase the size of the tank, right, of our reactant or product. And this can lead to essentially significant reduction in cost of the energy carriers that we generate, right, as we increase the size, where lithium-ion batteries, as we increase the size, essentially the cost is flat. And so this is very important to think about generation of energy carriers with hydrogen or with generating metals through electrochemical metal making, that we can generate energy carriers that we can use to decarbonize our buildings and the chemical industrial processes. So one of the scheme is we can store electricity in chemical form by reducing water, CO2, nitrogen, or metal oxides into the energy carrier, right? So during this step, we store electron energy to generate energy carrier and generate chemical energy. And during this step, we have oxygen evolution, right? Once we have the energy carriers like hydrogen, like metal, like small molecules of hydrocarbon or ammonia, we can either generate this energy carrier to convert to heat to replace fossil fuel in our existing energy landscape, or we can utilize them in fuel cells to regenerate the work or electricity. And during this step, we have oxygen evolution process. right? So these are very important chemical transformations if we want to have deep decarbonization of our buildings and deep decarbonization of our aviation heavy-duty vehicle, as well as the industrial and chemical processes related to mining, steelmaking, cement, and ammonia synthesis. So in summary, so going forward, we see really the challenges of developing batteries, advanced batteries, lithium ion, beyond lithium ion, lithium metal, multivalent are critical to further develop highly efficient, long-lasting, high-energy electrification technologies. Key to decarbonize aviation, heavy-duty vehicles, our transportation sector. They're equally important to develop electrochemical production of low carbon fuels, materials, and chemicals, where hydrogen production is central in order to generate the energy carriers. So once you have hydrogen, you can either combining with CO2 or combining with hydrogen thermochemically to replace fossil fuels to reduce CO2 emission with existing processes. Right? And so converting electrochemical and processes of oxide to generate CO2-free cement or a green production of metals. These are all important steps that currently we don't have efficient or cost-effective solution. Right. In addition, the negative emission technologies are also really important because we are going to have, power plant, a coal power plant that going to be operating into the decades, as well as in fossil fuel-based gasoline-powered vehicles, where 80% of the CO2 emission come from essentially the tailpipe. So having negative emission technologies is really critical to be able to capture the CO2 and then essentially convert them to useful materials and fuel. Right? So if you look across, all these technologies are needed to decarbonize, and fundamentally we can look at really a few processes are critical in order to advance the science as well as the technology. So we need to learn more and be able to design or control the surfaces or interfaces so they can facilitate many of the processes that currently are very sluggish, limiting the efficiency of conversion process. Right? We need to figure out how to design molecules so that we can essentially facilitate ion transport, facilitate electron, as well as charge transfer among the molecules. Now, for electrochemistry, right, so electron and ions are exchanged or transferred at electrode-electrolyte interface. So be able to understand the microscopically electron-ion transfer is efficient, was fundamental and key to control the energy transfer, energy generation in any of the electrochemical processes. Right. So we're going to be looking at examples and opportunities and challenges, how we can control interfacial processes to potentially advance our understanding of processes at these interfaces, which can provide solutions or step forward for various technologies discussed to decarbonize. So first, we'll be looking at lithium batteries, right? So lithium ion batteries, I would argue the future of lithium batteries, lithium ion and beyond, really is to advance these battery technologies, we need to learn more about interfaces between the electrode and electrolyte. For example, development of a solid electrolyte interface, SEI, between the electrolyte and graphite is a key enabling lithium-ion batteries. And stabilizing electrolyte, the oxygen electrode potentially is key to make metal air or lithium air batteries critical. And stabilizing electrolyte and lithium metal is critical to make practical rechargeable lithium metal battery technologies that can potentially double the energy density of lithium ion. So we're going to look at first examples of the interactions between the electrolyte and positive electrode materials in existing conventional lithium-ion batteries, how we can develop not only electrode materials as well as new electrolyte to advance and stabilize lithium-ion batteries. So if you look at the positive electrode materials, typically we utilize a late transition metal, lithium containing metal oxides. And the electrolyte we typically use are organic aprotic solvents, let's say cyclic or linear carbonate. Right? And if you look at the interactions between these organic solvents and late transition metal, and we know that these carbonate solvents or either linear or cyclic, they can become dissociated, absorbed onto the surface oxygen of metal oxide. And the driving force for such a dissociation can be as high as 2 eV. Right? As we remove lithium from these late transition metal oxides, as we increase the oxidation state. Right? So the process goes that the carbon of the carbonate absorb onto the surface oxygen, and simultaneously we strip of oxygen from the carbonate and absorb onto adjacent oxygen, and this proton or this hydrogen is converted into proton. And we have proposed and shown this process of dissociate carbonate on the late transition metal, the ability to do so to generate protic species is responsible for the degradation of nickel-rich compound for the positive electrodes. Right? So as we increase the nickel content in the lithium, nickel, manganese, cobalt, you can see the discharge capacity increases, but the thermal stability reduces, as well as the cycling stability. So the process goes as following, right? So we essentially have carbonate dissociate on surface and generate these protic species essentially by stripping hydrogen from carbonate, utilizing surface active oxygen on the surface of oxides. And this protic species essentially react with lithium-containing salt, lithium-containing anions, essentially generating HF and to reduce the surface transition metal oxide. And we have shown a direct experimental evidence for the dissociation process utilizing surface enhanced FTIR, where we can get at the surfaces of these lithium, nickel, manganese, cobalt compound during charge. And we can see how the surfaces interact with the electrolyte. And so we're looking at surface enhanced, so we're not probing the bulk of the electrolyte, but looking at electrolyte near the surfaces of the oxide. So as a function of increasing charging voltage, and we can see there's a growing intensity associated with VC, right, valent carbonate, and which can be generated essentially stripping two hydrogen from the EC molecules and form a double bond. And this signal is not present in the bulk of the electrolyte. And this is a direct evidence to show that at voltages as low as 3.8 or 3.9 volt, right? Really at the beginning of the charging for this NMC 811, we can generate protic species through dissociation of carbonate solvent on the surface materials. Right. So if we do similar measurement for NMC 111 and such dissociation or generation of VC or dehydrogenated EC is not observed, right? So this further supports report, essentially, this process is dependent on the surface electronic structure of the metal oxide, and specifically dependent on the surface oxygen activity, which can be described, generally speaking, by the bulk ligand oxygen or the bulk ligand p-band center relative to the Fermi level. Right? So as we essentially make the ligand p-band center deeper relative to Fermi level, the driving force for this process is reduced. Right? So essentially, driving force for the hydrogen absorption on the surface is reduced and become more positive. So any of these, for example, metal fluorides, nickel or cobalt metal fluorides, the driving force for hydrogen absorption is negative, is thermodynamically unfavorable, and the absorption energy is positive. And so that if we develop a fluoride coating on the surface, then this dissociation process will not happen. Right? And this is in agreement with if we coat fluoride on the surface of NMC811, then we see essentially we have a stable cycling relative to innate or bare NMC811. Not only we can change the surfaces to mitigate and reduce the surface reactivity or dissociation, we can also enhance the stability of the surface by changing the electrolyte. Right? So we can get rid of the carbonate solvent and utilize a solvent that is less sensitive to dehydrogenation. Right? Through the development of new electrolytes for lithium oxygen batteries, we have developed a new solvent molecule in collaboration with Jeremiah Johnson, where if you look at this sulfon-amide molecule that we essentially designed this molecule by removing any hydrogen that may be sensitive to dehydrogenation associated with, for example, oxygen radicals or associated with surface active oxygen. And utilizing this sulfon-amide electrolyte, it can be cycled with NMC811 without any visible or significant degradation, even in electrolyte, linear electrolyte conditions with respects to the positive electrode. Right? So this is essentially a example that how we can understand what might be happening, the degradation mechanism be happening on the surfaces or the interface, and develop solutions, either changing the solid surface or changing the solution in order to enhance the functionality or enhance the cycle stability as well as the energy of rechargeable lithium batteries. And what's really interesting with the system is that when we cycle the electrolyte with metallic lithium, we find this new electrolyte, sulfon-amide, and with the lithium FSI can also stabilize metallic lithium surface relative to the carbonate electrolyte. And utilizing carbonate electrolyte, we have essentially a rechargeable lithium metal surface, and that can grow or swell to 250 microns, where that with the sulfon-amide electrolyte, the rechargeable lithium metal surface electrodes remain intact or remain relatively compact. And so this is essentially another example or surprising example that changing electrolyte chemistry by controlling potentially the SEI due to the reactivity between lithium and electrolyte, that we can alter the morphology of lithium during plating and stripping, and which is critical in order to stabilize metallic metal surfaces going forward to double and the energy density of lithium batteries going forward. Right? And so much to be explored. Right? So if we put forward what might be controlling the morphology or stability of lithium metal surfaces with organic electrolyte, and we've seen the Coulombic efficiency, at least this is the idea we propose, the Coulombic efficiency of lithium metal stripping and plating, it can be described by a parameter or descriptor, which is defined is the kinetic of stripping of plating normalized to the lithium ion diffusivity through the interface. essentially not having too fast kinetics or too slow of diffusion give rise to the highest efficiency. Right? So this is essentially potentially point to a strategy is to develop liquid electrolyte that can stabilize metallic lithium to have high efficiency and also fast rate capability, potentially rivaling the development of solid state lithium metal rechargeable batteries. Right? So in order to further control the SEI, we need to know much more about the interfaces and how to examine the development of SEI and how to use electrolyte to tailor different SEI and how they may influence essentially the transport of lithium ion through the SEI. Which is all very critical in order to improve the safety and efficiency of lithium metal batteries. Right? So going forward, really electrolyte innovation underscore the further development of advanced battery technologies. And going beyond the lithium ion batteries, which I think there's plenty of opportunity to look at sodium batteries, which we have more, sodium is more earth abundant, right? So sodium batteries are very critical potentially for stationary application. Going beyond lithium and sodium, if we look at multivalent metals, right? And especially if we look at aluminum, right? Aluminum is the most earth abundant metal, and is also among the metals is the cheapest metal, is worldly distributed. If you look at the energy density for aluminum, either utilizing aluminum ion batteries or utilize aluminum rechargeable batteries, it provides the highest energy density. So the challenge is how do we develop electrolytes and so that we can stabilize a rechargeable aluminum or allow reversible stripping of aluminum and the plating? And how do we develop electrolytes so we could have essentially a positive and negative electrode give rise to a sufficient large voltage in order to utilize aluminum either in aqueous or non-aqueous electrolyte. So with aluminum, the challenge in aqueous electrolyte is how do we suppress the parasitic reactions of hydrogen evolution when utilize aluminum? So many of challenges ahead in order to advance battery technologies, and where the key and understanding surfaces, understanding interfacial phenomena is critical in order to develop multivalent technologies. So now we come back to the generation of energy carriers. Right? So if we think about how to generate energy carriers, which is absolutely critical to replace fossil fuel, right? To provide heat, right? So significant sort of the carbon or CO2 emission in our industrial and our buildings, it comes from really generation heat from fossil fuel, right? So generating carbon-free or carbon-neutral energy carriers through electrochemical methods is critical to decarbonize. So we can think of processes of transforming these molecules electrochemically, reducing water to generate hydrogen, reducing water, nitrogen to generate ammonia, right? Or reducing CO2 and water to generate hydrocarbon. And these are all very important processes to consider and to develop. And scientifically, we don't quite understand mechanistically how to control the kinetics and how to influence the barriers for such a transformation. So therefore, many of these reactions, either oxygen evolution, oxygen reduction, generation of ammonia, nitrogen activation, CO2 activation, tend to be very sluggish and give rise to very large voltage loss losses or energy losses, and which make the practical use of these applications very challenging. Right? So the trick is how to develop catalysts, either solid-state heterogeneous catalysts or molecular catalysts, that we can interact with the molecules we want to activate and reduce the barrier. Right? So one example we'd be looking at is how to, again, control the oxide electronic structure so that we can influence the oxide interactions with molecules, either water or oxygen or oxygenated species, to facilitate transformation and reduce the barrier. So we will be looking at essentially extending the thinking of interactions between oxide and carbonate, where the example of lithium-ion batteries is to reduce the surface oxygen activity, so we reduce the interactions or dissociation of carbonate on the surfaces. For the context of catalysis, where we want to design the oxide electronic structure, we want to enhance the surface activity, oxygen activity, allow stronger interactions with molecules to facilitate the kinetics of chemical transformation. Right? About a decade ago, Dane Morgan from University of Wisconsin and I have proposed that if we change the oxygen p-band center relative to Fermi level of the metal oxide. Right? So essentially by changing in a series of perovskites, either changing the A site or changing the B side ion, we can change the Fermi level relative to the bulk of oxygen p-band center. And we find either for surface exchange, right? So essentially it's exchange between O2 and O2 minus, which is a critical reaction in solid oxide fuel cells or solid oxide electrolytic cells. You can see by pushing the Fermi level into the oxygen p-band, we can significantly enhance the exchange kinetics by 6 orders of magnitude. Right? And that indicate this parameter or this descriptor can be a primary descriptor influencing this activity. And similarly, if we look at the oxygen evolution in basic solution, right, where we can oxidize OH minus hydroxide ions by stripping some electrons and protons to generate oxygen molecules, we can also increase the activity for a series of cobalt oxides by 2 or 3 orders of magnitude. Right? So in these graphs, essentially the lanthanum represented in L, M is manganese. So essentially from the bottom to top is we're going from manganese to cobalt to iron compound, where the valence state of the transition metal is going from 3+ to 4+. Essentially, we're pushing the Fermi level into the oxygen p-band. And we've shown this can be used to predict new oxides with high oxygen evolution activity in different environments. And this correlation first proposed based on computed oxygen p-band center, and later on was also shown to be validated experimentally by measuring the electronic structure of these metal oxides, utilizing X-ray absorption and X-ray emission spectroscopy at the advanced light source. So increasing this oxygen p-band center, right, pushing it closer to the Fermi level is important to enhance the catalytic activity. It can also push it to decreases its stability. Right, so it's really regulating the stability as well as increasing its activity is critical. So by playing with the covalency, right, so one can enhance the covalency and while maintaining its oxygen p-band center, we have developed this new compound of bismuth strontium cobaltite, and that is stable on the surfaces, oxygen evolution, as well as exhibiting a record low overpotential or record high oxygen evolution activity in basic conditions. Right? So this is one example how one can play with oxide electronic structure and control essentially the interactions between oxide metal and oxygen side, how they interact with OH and how they facilitate deprotonation of OH species to O and OOH and facilitate oxygen evolution. Right? And this surface toning of oxygen site has also shown to be very important in facilitate oxidation of NO to NO2. So NO or N2O is a well-known greenhouse gas, or it is a air pollutant. For example, if you have a significant fraction of diesel-powered vehicles, NO can be a well-known air pollutant. So improving the air quality, we need to have effective catalysts to oxidize NO and to convert it to nitrogen or to store it as a form of nitrate. So we have shown recently also through a series of perovskites, lanthanum strontium cobaltite, right? So if we increase the strontium content, essentially increase the cobalt oxidation stage from 3 to 4, and you can see we can increase the NO absorption on oxygen. And what's really interesting is we show that NO will not absorb onto the B site. And this suggests that B site, or the cobalt metal site, is not the active site for NO oxidation to NO2, but oxygen is the active site. And if you increase the strontium content in this material, or push the Fermi level into the P band, we can significantly increase the binding strength. And in fact, this NO can absorb onto the surfaces, in fact, pulling the surface oxygen out of the surface to form more of NO2 moiety. And similarly, the NO2 can also grab the surface oxygen and pull it out of the surface to form more of the NO3 moiety. And such a computated trend was also validated through ambient pressure XPS at ALS. As you can see, as increasing strontium content, we see this NO absorbed onto the oxygen side, speciated in particular this peak detected in the nitrogen 1s spectra indicate that we have more NO2. And when we have strong enough binding, we can also form a significant amount of NO3. And NO3 is so strongly binded that it's essentially poison at the surface, because the binding energy of NO2 is greater than 1 eV at ambient temperatures. Right, so by controlling the binding energy of NO onto the surface, and we can see that we look at the kinetics or turnover frequency of NO to NO2 oxidation and exhibit essentially a maximum at intermediate binding. Right? So we want to have NO bind to the surface, not too strong and not too weak, and to have the highest NO oxidation activity. So in fact, this intermediate strontium 0.2 has one of the highest non-precious metal oxide activity for this particular reaction. And this high catalytic activity can be explained by the following mechanism, right? So we can essentially tailor the surface oxygen activity to have NO absorption. But this absorption cannot be too strong, and we can essentially also want to desorb as a NO2 moiety and generation of oxygen vacancies. So it's really the competition between a strong or reasonably strong absorption and the low enough penalty to generate oxygen vacancies is the key in order to essentially develop a minimum energy barrier from NO to NO2. Right? So this is another example how we can tune electronic structure, tune surface oxygen activity to enhance the kinetics of various reactions. Not only we want to look at the correlation, right, between the electronic structure and the catalytic activity, and we know correlation is not causation. We also want to know at atomic level, on the molecular level, how does, the processes, what are the reaction intermediates? Can we detect the reaction intermediates? So therefore, developing electrochemistry, electrochemical understanding on single crystal, well-defined surfaces is really key. And developing in situ measurements where we can probe processes at electrified interface, and coupling with density functional theory of the electrochemical conditions is very important. So we are particularly interested in understanding how would, let's say, an oxide or metal surfaces interacting with electrolyte, and what are the interactions, how would the interactions would change the absorption of species, might change its function of voltage. And we utilize a technique is called in situ surface X-ray scattering, where we use glancing X-rays and get at essentially the single crystal of the oxide. And this is a data of ruthenium dioxide, where as function of voltage, we can scan essentially the surfaces and look at how the diffraction peaks will change its functional potential. And by looking at the spectra that are sensitive to scattering of oxygen, we can essentially probe the surface sorbate species. And we can observe the surfaces initially absorbed onto, let's say, the ruthenium calcite with fairly long bond with ruthenium oxygen, gradually with increasing voltages, and we see that the bonding strength is reduced. And this is indicative of deprotonation of water to OH and then to O, and essentially we see the formation of a dimer onto the calcite. So using such a technique, combining with density functional theory of interactions of water as function of voltages, we can see under oxygen evolution conditions on ruthenium dioxide surfaces 110 at a condition of 1.5 volt, we can see what would be potentially the limiting step. And we note that at these conditions for these surfaces, it's really the deprotonation of this peroxo species absorbed onto the calcite, and that's stabilized by a proton absorbed on the nearby oxygen on the bridge side. Essentially being able to deprotonate this particular step would facilitate essentially oxygen evolution. Right. And this is really important to understand because we can see what might be real limiting. Now, if we go from a 110 surface to 10 surface, and that's essentially the energetic indicated by the blue line, and we significantly destabilize essentially this absorbed OOH group onto essentially also this calcite on the 10 surface. And we essentially make the conversion of O to OOH relimiting because it becomes uphill. And through this process, we can see that 100 surface should have higher catalytic activity. Right? So if we, by varying different surfaces and probing what may be on the surface under operating conditions, we can tune the active sites, we can tune what might be limiting on the surfaces and reduce the barrier. And this can be validated also by looking at surfaces that potentially further weaken the absorption of O, further absorption of OOH, where essentially the energy barrier from O to OOH is relimiting and further reduce the catalytic activity of oxygen evolution. And you can compare the computed trend going from 110 to 100 to 101, right? And we're on either side of the volcano, we have a different relimiting step. And this trend is supported by experimental measurement of single crystal surfaces. Right? So this further provide molecular details for what might be limiting, what are actually the species on the surfaces, and that can allow us to develop strategies, how to change the surfaces, as well as how to change the electrolyte. right? So far, we have been changing how would the surfaces really changing the binding energy of OOH or OH onto the surface, right? And we having such information, we can also think of strategies in the electrolyte, right? Because each of the step, not only we can control the binding energy of OH, we can potentially control the barrier, how electron and how proton it can be transferred to these surface species and further enhance or tune the catalytic activity. And that's what I'm going to show in the next few slides, right? So how to change the chemical physics of the liquid electrolyte so we can facilitate and control electron and proton transfer. And this is really key, fundamental to all processes in nature and in life. And this is also the processes, these proton-electron coupled reaction or proton-electron coupled electron transfer is key to generation of energy carriers, hydrogen, carbon dioxide reduction, and nitrogen. Because to reduce all these molecules in aqueous electrolyte, it requires proton-electron transfer reactions. So this is also a very critical topic if we can facilitate or understand how to tailor the energy transfer or the proton transfer from proton donor to acceptor. We can also tune the catalytic activity. And there's very interesting interactions between, let's say, ions and water, and to generate non-covalent, right? So these interactions much weaker than the absorption of OH on the surfaces. Right. So these are on the order of, for example, 0.1, 0.2 eV versus absorption energy typically on the order of a eV. Right? And we want to demonstrate examples of controlling very weak interactions, non-covalent interactions by altering the water structure, by altering the solvation environment of near the anion redox or near the active redox, we can change the electron transfer or proton electron transfer rate significantly. So first example is iron cyanide redox, right? So this is one electron outer sphere reactions, very fast reactions. If we essentially add lithium, sodium, potassium, or cesium to these redox centers and to classical MD. So we know near these anion redox center, the solvation environment is very different. And we have essentially in the case of lithium, we have more water solvating, fewer lithium. In the case of cesium, we have more cesium solvating and fewer water. And this bulk studies using classical MD is also shown can be translated to interfacial on the surface of platinum, on the surface of gold, at a relevant potential for redox of the species. And this is surface enhanced FTIR, where you can see in the case of lithium, we have essentially more of ice-like water or hydrogen bonded water. In the case of cesium, we have more isolated water. Right, supporting a very different interfacial structure in the case of lithium, in the case of cesium, where we have more cesium closer to the surface. And having cesium closer to the surface and fewer water, essentially we can bring the anion redox closer to the electrode surface and facilitate the electron transfer. In the case of lithium, due to the presence of hydration layer, essentially the redox center is further away, and that leads to a greater distance of electron transfer and leads to greater reorganization energy. Right? We can essentially measure the kinetics of such a reaction in presence of these different cations, and we can model it using Marcus-Hutchinson formulism, where we can extract exchange kinetics. We can look at the exchange kinetics for these different cations, can vary by orders of magnitude. And we can also extract the reorganization energy. And you can see in the case of lithium, we have much greater reorganization energy facilitated due to the larger distance for electron transfer. And such reorganization energy can be modeled through the Born model based on the solvation environment that we have, reflecting very different dielectric constants. So this is one example to suggest, even for this simple reaction, although we understand the composition of the solution or redox species in bulk, there's very little we understand about interfacial solvation environment, which can be toned greatly by modifying ions and the surfaces. We can also show that through the same cation dependent solvation environment, right? But we can see they can alter the kinetics of hydrogen evolution, right? So this is, we're reducing water, and essentially we need to have proton-electron coupled reactions to generate absorbed hydrogen. Essentially that leads to a combination of two absorbed hydrogen to generate molecular hydrogen. By altering either pH or by altering the cations in the solution, we can tune the kinetics of this reaction by 2 or 3 orders magnitude. And this large change in kinetics is happening on the same, essentially, surfaces, right? So we're not changing the platinum surface. All we're changing is the interfacial structure. And what we find is when we have hydrogen bonded water, in the case of lithium, it can facilitate the proton-electron transfer to generate the absorbed hydrogen species. Right? In contrast to the case of cesium, where we have only isolated water, where the barrier for electron transfer and proton transfer is greater. And so this is another example of how we can essentially change the interfacial structure and tone the barrier. In particular, in this case, is really the entropy associated with proton transfer involved in this proton-electron transfer reaction. And so this publication has appeared in JACS Gold a couple months ago. The last example I want to show is in the case of oxygen reduction. Again, this is in the case of acidic environment where we change the surfaces between the electrolyte and platinum surfaces using a layer of ionic liquid, where we can tune the pKa of ionic liquid. And we find the oxygen reduction activity on the platinum surface, either nanoparticles or planar surfaces, the peak catalytic activity, or generally speaking, the catalytic activity can be enhanced up to 3 to 5 times. And the peak of that enhancement occurs when the pKa of our ionic liquid versus the pKa of the surface adsorbate in the rate limiting step matches. Right? So when the proton transfer is in resonance between the proton donor, which is our ionic liquid, to the proton acceptor, which are reaction intermediates, in the rate limiting step for oxygen reduction, we have peak catalytic activity. Right? So this is really just another example of toning proton activity near the electrified interface to tone the catalytic activity as well as tone selectivity. So this is, we believe is a very interesting direction to explore, because we can utilize utilize toning of such interfacial solvation environment to potentially suppress hydrogen evolution, right, which is needed in the case of CO2 reduction, right? Because for CO2 reduction, we generate multiple species simultaneously in a very similar thermodynamic voltage, where kinetics of hydrogen is the fastest, where the generation of other species are slow. So it's very important for us to be able to suppress hydrogen selectivity and catalytic activity in order to make the product low carbon fuels through this process. And this is also really important to enable electrochemical nitrogen activation, right? So either in aqueous environment, most of the measurement, with the exception of utilizing lithium metal, all the experiments shown to date, a very small amount of ammonia has been detected. And this is, again, has to do with, to activate nitrogen electrochemically, we have to go to very reducing potentials where generation of hydrogen is prominent. And so suppressing hydrogen evolution and be able to facilitate proton transfer associated with nitrogen or surface nitrogen species is critical. So I want to essentially just end to say that I show you an example based on essentially this idea of hypothesis-driven research. And going forward, I think it's really important to also do a data-centric discovery, because so far our research in scientific molecular discovery of materials or molecules has been focusing on depth, not breadth, right? So there's over 10 to the 60th potential materials or molecules to be discovered, and we have only exploited a very tiny fraction of it, right? So this is analogous to mapping a few hundred years ago that we might map the coastlines very well, it's well understood material, that there's a large, essentially territory frontiers and to be explored. So essentially coupling the hypothesis-driven research and with the data-driven research may allow us to minimize some of the intuition bias, allows to traverse greater compositional space, facilitate and accelerate our discovery. So this is, one example that we're using high throughput electrolyte making and testing using robots coupled with MD, DFT, and machine learning to accelerate electrolyte discovery. So again, I just want to conclude, there's many opportunities and challenges in order to decarbonize. And this is really exciting topic to work, not only from the science side, but also from the technology development, as well as from techno-economic analysis, and also from the policy side. And all these aspects are critical in order to allow us to quickly decarbonize in the coming decades. So I want to just thank you for your attention and be happy to answer any questions.